Yes, so Jürgen Hackl is today discussing agent-based modeling in regards to simulations of epidemic spreading in urban areas. He is a lecturer at the University of Liverpool and a member of the data analytics group at the University of Zurich. Much of his work has been on improving the understanding, design, and performance of complex independent systems. Has been investigating how this can be used to decrease the complexity of computational models. So yeah, without further ado, go away, go ahead of it.
Thank you very much. And also thank you for giving me the second opportunity to talk at the Risk Institute online Zoom talk. Today I will talk about agent-based simulations for epidemic spreading in urban areas. This presentation, also this work is, I guess, quite a brand hot topic. However, we, also together with Thibaut from ETH Zurich, we conducted this in 2018. And this was a small presentation we gave in Cambridge on a symposium for network science. So this talk won't be as long. It would be probably 15 to 20 minutes. However, I'm looking forward to a in-depth discussion, and maybe we can also see where this leads us. So I guess the topic is, as I said before, a hot topic now in research, how to deal with epidemic spreading given the coronavirus. And our interest actually, let's see if it works. So the motivation for our work was actually when we commuting to work, to university, or going shopping, we're using public transport, especially in Zurich, where I did my PhD. And normally the public transport is very crowded. And the question arose was, when someone is sick and using public transport, do we have a higher chance in order to get infected in such close proximity with a lot of strange people? I guess don't have to show you this, but 2018, this was not as common as today. How to prevent flu spreading, and I guess now with the coronavirus, we already knew that we should keep our distance. We should wash our hands. Yes, this was also 2018 still valuable information, and we will also see and explore how those circumstances change. Also, when you increase the distance or decrease the distance, how does this affect the epidemic spreading? And as I said before, the main motivation was to see how actually epidemic spreading, in this case influenza, so the seasonal flu, spreads considering public transport, so when people are cramped together. And we found one paper which was published 2011, where they did a small study with I think approximately 72 cases on influenza, and they figured out that it might be up to 6 times higher the risk of getting an infection when you're using public transport. And we thought, they did this based on a case study. Can we do this on a numerical way and see what we came up with when we simulate more or less the interactions between different people? And we decided to go with MATSim. This is an agent-based transportation simulation. So it's actually designed for engineers, for transportation engineers, in order to study the transportation patterns, in order to plan new roadways, in order to optimize bus schedules and see which might be the right fare on using a highway. And nowadays also more and more important is when we now come with autonomous vehicles, how does this fit into our daily routine? So as I said, that the main idea of MATSim is actually not targeted to see how epidemic spreads. However, we hijacked this model and adapted it in order to allow such simulations. Maybe also what I should say here is the presentation I gave you wrote a small paper and the code is online. So if anyone is interested in running the simulations by themselves, MATSim is open source, and also this very simple script we wrote is also available online. Yeah, maybe to the agent-based model itself. So there are different types of agent-based model, and in MATSim, what we simulate here, what an agent is more or less an individual person, and this individual person more or less has a daily plan. So a person can be an adult, a child, a member of a family, and they have every person has its daily plan. And for instance, here, very simplified, we have this spatial network where a person starts at 7:30 in the morning at home, then takes his car, brings his child to the kindergarten, takes from there the public transport, go to work, after work, going back, picking up the child, going grocery shopping, then spending some time for leisure, and then going back home. So this is more like a daily routine, what the people are doing. And in order to do this and to all these activities, people have to move around in an urban system, and they using, as indicated here, public transport. They can walk, they can cycle, they can use cars. And so they have a daily plan and they have to fulfill the plan. MATSim, what they're doing is to see how can they do this, what is the best mode of transport where each agent will be most satisfied with. And important thing about this is to get those agents, and they are normally created from a synthetic population. So this is a quite difficult task in itself to get such a synthetic population, and many factors play into account, and there are different models to do this. So what we have to create is more or less, we have, for instance, in the global metropolitan of Zurich, there are roughly 1.5 million people, and with this synthetic population, we have to get a good estimate about how those people, where they're located, what is their age, their income, do they own a car or not, where does they work. And this synthetic population requires a lot of statistical modeling on diverse tasks, but also it's based on observation surveys and so on and so forth. So yeah, for today's talk, I won't go into much into the detail, only to give you some indication what was used in this model and what might also be important for epidemic modeling, since those are very critical factors. So the age, for instance, if you're an elderly person or if you're a young adult, your living situation, your social status, your income. So these are important matrices we can later on use in order to model this epidemic spread. And as I said before, MATSim is mainly used for traffic simulations, for traffic planning, traffic engineering. However, it gives a quite wide variety of use cases you can do, and I picked here some from the homepage. And in the next one, I will show you more or less the power of MATSim in itself. So for the next example, I will take this Germany example as a small video. I'm not sure how well you can see it with this streaming via Zoom. However, I tried to explain what's going on. So what was done here is using MATSim to model whole Germany and all the transitions between the bigger cities. So what you see here, these dots moving are the single agents, which are moving towards different cities in order to fulfilling their needs, as I said before. So they're going either to work, they're going to shopping, they're bringing the children to school, or they're going itself to school. And when, so the simulation starts at midnight and then goes 24 hours. And what you see here popping up is now the activities that people are doing, and then moving on. And you see, you can simulate quite a large scale of networks. So in this case, the whole Germany, what the agents are doing. And as I said before, what we have done, we use this model, not for Germany, but for Zurich. So this is now Zurich, where we tested now out this epidemic spreading and saw, look more into how this spreads in a spatial-temporal environment, but also how the use of public transport might affect the spreading in itself. So what you see here is the city of Zurich. I'm not sure if I have a pointer, but at the bottom, so in the south, in the middle, is the Lake of Zurich, and above is the city center. And what you see here in gray are susceptible persons. So that's our agents, which are starting and popping up on the map during the day, more or less. So this is this synthetic population, which is used to model the people using the public transport, but also using the cars and bicycles or walking paths. And what we have done now here is we added an infected person and said, oh, this person is infected and can spread the disease. So the disease spreading was modeled with some very simple probabilistic model. So when another agent is in a certain range, a certain amount of time, then we assigned probability that the virus will spread from one person to the other person. So that was more or less the very simple model. Later on, we used real-world data recorded from the influenza from 2016 to calibrate our model, but more or less that's the whole idea. So very simple model. Of course, there's much more which can be improved. As I said before, there's all this nice properties like age of the agents, income or living conditions, and so on and so forth, which was not considered here. Purely the distance between two agents and the time they spent together were considered, and then there's a certain probability that the influenza virus can be transmitted. So let's start this simulation here. Again, this is only one sample, so this is one scenario. Of course, we run multiple simulations where different proportions of the population is infected, and this was also randomized. But this is now more for illustration purpose. So we have one specific agent which is now infected in red, which is in the middle of the map, the northern part. And let's see. So now people coming to work, Zurich will be crowded. We blended out more or less the other agents so that it's not getting too messy. And then we see already the first people are infected, they're leaving their work and going home. And the typical cascade more or less begins to start. And so this is now after one day. So you see people are moving away now, they're going home and disappear from the transportation network. So we highlighted then here more or less the agent after one day, which are infected from one person here. And of course, we can do this simulation over, again, over multiple time periods. And when we do this, we're getting this graph here. So this was the graph for the first day. So we start with one infected agent and he had the chance to infect 50 other agents in this simulation run here. And when we continue over time, what we're ending up is, so the next day, the infected agents, again, going back to work, meeting other people, going shopping, going to university, and we're seeing this increase, what we also saw with the corona virus. So what we added then now is also the possibility that an agent get recovered Oh, that's the next slide. So, yeah. So the first one was, now when we do this, we can do this for a longer period until we reach more or less an equilibrium. Then what we added is the recovery. So with a certain probability, after a certain amount of time you had the virus, you getting recovered. That was, again, very simple assumption, very simple probability we assigned to each agent when they were affected. After a certain time, the probability that you are recovered increases more or less. And of course, when we have this, then we're getting this classical curves. What we also can model with this classical SIR model. So here in the bottom graph, you see the dashed model, which is representing more or less the theoretical model, and in red you see the agent-based simulation. So far it looks quite similar. However, this was more like a dummy example where we picked one agent and tried this out. However, in reality, the data looks something like this. So this is now the three cases we compared. In blue, you see the real case. So this was the seasonal flu in Zurich, recorded by the health organizations here, the doctors. In red, you see the simulation, what we performed. And in black, again, the dotted curve is the SIR model. And also we were quite surprised since we already got this very, very simple model, those results. And of course, there might be improvements, how disease spread if the age is taken into account, and so on and so forth. And since I'm interested in networks and do a lot of research on networks, this problem also can be converted to a spatial-temporal network problem. So we don't actually need to trace the, I guess nowadays we need, but in this case, the idea was not to trace each individual path, but we more or less collect where they meet and when they meet. And then we're getting a kind of temporal network. So what you see here is the first agent I showed you, which was infected. He infected more or less as this cluster at home. Not at home, sorry, the cluster at work. And then people after work went home to their families and infected their family members and friends, which they were in contact with in a later stage. And these are the first 50 people what you saw in the animation for the first day. So this is this temporal model, what we can use for speeding up more or less the simulations on spreading the virus. And last but not least, the question at the beginning was how strong does the public transport actually influence our epidemic spreading? And we came, also with this simple simulation, we also the simulation showed us that we can expect 2.5 to 3 times more infections when you're using public transport. So it's less than the 6 times higher what the other paper came up with, but it's more than when you're using your car, more or less. So there is a higher chance, more or less, to get infected when you're using public transport. And I guess that's the reason why we should wear masks nowadays, in order to avoid those spreading. As I said, this talk was rather short. It was more, I guess, more like a starter for further discussion. And I'm happy if there are any questions to answer those questions. But also, if you're interested in the modeling or develop the model further, or have some other insights what you'd like to share, I'm happy to listen. Thank you very much.
Right, yeah, thank you. Just a note that if you have a question, you should be able to select the hands option. So you put a hand up, and I know that is a question in line. Um, yeah, I have a start question which might be inappropriate given the scale of the model. But when I've communicated with some epidemiologists about transmission, a lot of the focus or concern seems to be less with the area, for example, exhaled droplets might be in, or more about how transmissible the vector might be. For example, atmospheric travel or surface travel. And I was wondering, is that a level of complexity that is considered or can be considered, or given the scale model, is it something that should be considered? Um, that's a useful thing to have in this kind of model at all. Like this, thinking on what kind of whether you should include that kind of vector of transmission. Maybe you mentioned it before. I didn't actually might have captured it, but
As also said at the beginning, this model, also this agent-based model, was never designed for epidemic spreading. So it's really designed for making predictions about the future of traffic. However, the traffic engineers did a lot of work, spent a lot of time to calibrate the models to get the most accurate representation of our traffic flow, of our mobility data, what you can more or less model. That's more or less the main point of this. And so the idea was only to hijack and more or less getting these contact networks out of how the mobility patterns of the people. Of course, when you can track cell phones, I guess you're getting better data. However, this is very hard to obtain, first of all, and also to test hypotheses. It's quite difficult since you have the data once, and here you can test out different setups and see also different strategies. So like banning transportation in public transportation, limiting the amount of public transportation. However, they said then that the backlash that more people will use the car, they don't find parking spots, and so on and so forth. But I think it's not very so it's a precise epidemic model what you were looking for. So I guess it might be implementable since it's open source and everyone can change the code, but it was not the purpose. So the purpose was really this mobility data and this social contact interaction data.
okay, yeah, sure, thanks. Alex, I think you have a question.
Yeah, I guess in terms of modeling like the mobility of each individual, have you looked at is there a way to implement a scenario like lockdown or isolation for the individuals in these cases?
Yes. Yeah.
And have you like, is it simple enough to sort of set up a situation and see the impact of different like lockdown and isolation strategies in these populations?
Yes,
are you missing the phrase? Sorry. Are you missing the phrase testing strategy in there, Alex?
Well, testing is not a part of this model, is it?
No,
No, but that's
no, that's true. Also, as I said, this model was developed 2018, so
yeah,
we never had in mind to lock down people. It was more like really to see if there is a difference when you're using public transport net, how it can be implemented. So I know this was implemented for other cases. There was some cases, also not for epidemic spreading, but what was it? When there's a nuclear accident or something like that, and then how they should behave, which you should communicate your strategies and stuff like that, and then people reacted according to the information they had. But it's possible. So you can change the behavior of the agent and say, okay, they stay at home, or you should lock down a certain factory and then all the people there stay at home, and then you can see. I guess that's not so difficult to implement.
Yeah, that'd be really, really interesting to have a look at them. Thank you very much.
Right, that's a nice short question. Next, we have Adolphus. If I ask you a question.
Yeah, cheers, Simon. Good afternoon, Professor Jürgen. Thank you so much for your insightful discussion today. I think it's a really interesting software that they just demonstrated for us. And I basically have two questions. The first of which is have you already attempted, or will you be planning to attempt to study other cities with high population densities in the context of like this pandemic situation, such as like Hong Kong or Singapore, for instance? And my second question is like, would you foresee this? And I think this most probably being used for like crisis management and some sort of like a crisis management platform.
So maybe I should mention, so this was more like a side project from my side. So it was more like playing around, and I needed some temporal network. So that was why we decided to look into this aspect. So it was never my main focus of research for the first part. So we only looked at the Zurich area. There are other more available cities out there. I think also now Rio and a lot of other bigger cities, which can be downloaded from the homepage and tested out. And to the second part, yes, that's more of my interest, but it's not about epidemic per se. So since I'm doing anyway, working on infrastructure systems, and then there's a critical question, how to evacuate people in order that they don't clog up all the roads, or how to communicate information so that people stay where they supposed to stay, or where they, in order to lead them where they should go. And this is active research, yes. More like on influencing the agents in the most optimal way so that they do something in order to benefit the whole population. Which can either be staying at home, locked down, or don't use public transport, or move to this place or move to that place.
Sure. Well, thank you so much for your views.
Okay, if was that both questions asked? Yeah, I assume so. Right. Yeah, so we've got another question by Paul.
Hi, Jürgen. That was a really interesting talk. I work over in geography, so I've looked at some of this kind of simulation modeling from a different angle. So I had a whole bunch of questions. Stop me when you got bored, but
okay, no, come.
Zurich population, I just looked it up, is 1.4 million. Is that roughly what the size of the problem you're working with?
Yeah, exactly. Yes, yeah.
You had 1.4 million agents, or less?
Yeah, we scaled it down since we only use 10% of the whole population for this run I showed you. Otherwise, it would be cluttered with agents.
Yep.
And also then when you increase the number of agents, the computational time increases dramatically, since you have to find the optimum and so on.
That was my next question. So what was this kind of computational resource and runtime? So what did you need, like a machine, or is it just a desktop?
We run it on this with 10% of the population on a desktop computer, roughly 2 hours per simulation, which were 100,000 agents, more or less. Yeah. You can use the software on a cluster, so they provide also multi-core usability, and yeah, then you can scale this up. But I know from colleagues, so we have also the ETH has also the model for whole Switzerland, and they run it once for 8 million people for 1 day, and this runs over 2 weeks on a high performance computer. So yeah, so there is also need in order to speed those calculations up. And one idea, and what we are working on, is using temporal networks, spatial temporal networks, in order to simplify those simulations, because often we don't actually need where they're actually going. We need where they more or less might be and when they might be there. And a lot of the time, or the time-consuming part here, is really to figure out which is the most optimal route the people can use in order to utility.
But if you go down that route, does that mean you lose information about who's going to be sharing the same space at the same time?
Yes, yeah, you lose a little bit there, and also what you lose is this is why transport people don't do this, is where when the people are on the road to which point in time, because they like to predict traffic jams and congestions and stuff like that, which you lose more or less. But you're getting more or less where the people might meet with a certain variance and when they meet. However, you don't have this very precise information. Maybe also for the information, so the MATSim now, what we used is a time scale of 1 second. So every second we got the GPS or the coordinates of an agent and the activity, what he or she is doing. So it's a very high resolution time scale.
Yeah, it's very high, isn't it? That'd be an easy way of saving time, is to scale that down there.
Yeah, I guess so. Yeah.
So you had a starting scenario. Well, you had multiple starting scenarios, but if you had a starting scenario, did you run that same scenario multiple times to kind of get the average behavior, or did you just take a range of different scenarios and run them once each?
No, we took a range of different scenarios and run them then once each. So there was a certain probability that I think also here what we used was we uniformly distributed more or less a certain amount of population got the virus, and then this was uniformly picked from all the agents available, and a scenario ended then more or less when there was a stable, after a while when we say, oh, there was no big changes, so we stopped this then there. But we never think we didn't run a scenario multiple times.
Because in theory, because it's a sort of Monte Carlo
exactly
process, in theory you need to run it lots of times. But I guess if you run lots of different scenarios and you draw a graph connecting the points from the different scenarios.
This was also what I didn't show. It was the uncertainty bounds of this. Probably I should have added this. When we're using a simulation approach, of course, we're getting not only this one scenario, what you saw, but we're getting a bunch of them, and which are more severe and less severe. So in the paper, there is this given. So there we have also the uncertainty bounds and what we used for the simulation, and also the parameters we estimated. So this infection probability and the discovery probability, which was more or less based on the data we observed here in Zurich.
Yeah. My final question was, it's the thing I've done some work on, is synthesizing populations, your starting population. So could you talk a little bit about that, or is that some data you took from somewhere else?
So I didn't do this here because it was done by my co-author Thibaut from ETH, where they're focusing on the Department of Transportation, and what they are using, so far I know, is they're using a Bayesian network approach in order to synthesize the population. I think, let's see if we can go back and edit what we used. The bottom, there is the...
Yeah, you had a little brief description.
Yeah, so let's see what... So this was... it's Impress, but it's implementing Bayesian network and generalized ranking model for IPF construction problem. It should be out now. So since, as I said, this is an older presentation, this should be out now. But also the code and all the stuff what Kai Axhausen's group at ETH is doing is online on MATSim. So if anyone is interested in using those models, it's available there.
Right, thank you.
Right, thank you. I'm not sure we have any more questions. I just want to clarify that you said it's open source, so anyone can access it and work on their own code. Did you say it was on MATSim where it was?
Sorry?
Was it on MATSim if people want to go?
Yes, MATSim. Yes, yeah, MATSim. I think it's matsim.org, or let's see if it's here. Not sure if it's matsim.org or MATSim. I think it's matsim.org.
Okay, sure. I'm sure it's pretty quite easy to
But
find.
yeah, MATSim, and this gives you also the examples Where do I have it? Those examples are also, I took them from their homepage. So they have multiple use cases and simulation. And yeah, they are now preparing so some of the data here in Switzerland are confidential, so not confidential, open for research. So you have to sign that you're using it only for research, because other people use this commercially, and so there is this. But for research, there you can normally get the data, and now they're preparing also a lot of data for open source, where they which can be distributed freely without getting any third-party consents.
Sure. I think in the UK we have similar kind of access to land data anyway, but I think there's also quite a lot of open source data here as well. So I think it would be quite easy to kind of transapply that.
I think there's some great examples from London. I'm not sure if it's on here, but I think there's a group who is working with this in London somewhere. So there's a huge London metropolitan area with public transport and roads. However, again, so the main purpose is for transportation. However, there might be nice features which can be used also for other disciplines and going a little bit more interdisciplinary. And those tools might help to answer those questions. I think that's the main idea of those, I guess also of this presentation, to showing that with tools from one discipline, we can also address problems in another discipline. And so
sure.
I guess we should keep an open mind, I guess.
Yeah. So we have another question from Scott.
Hi. You sort of were at pains to say that this wasn't built to be prognostic for the pandemic, but in fact, you have more detail about the networks than are used in those more sophisticated pandemic models, don't you?
Yes. Yeah. So I guess the networks are more on. So the more epidemic models, I think they're not using this very fine-grained where
Right.
people are on the road and so on and so forth. So they're more using, you have a housing here, and then there's some exchange between those. So the different types of network models doing
Right.
those.
So they're probably doing statistical or stochastic models for the connections. And so it seems to me that what you guys should do is, you have a brand new roller skates and they've got a brand new key, is to come together so that you can have a better time, right? I mean, because that detail will make a difference in the epidemiological model, I suspect.
Yes,
Certainly.
yeah. We were also talking to some epidemiologists about this. Of course, they also see some improvements which are needed for this model. For instance, here, what we're interested in is only an average day, more or less. What they're interested in is the change between weekday and weekend, and also what they're interested in is travelers. So when they're coming from outside into the system and leaving the system, which is somehow considered here, but not in the detail they would like to have.
I see. So you are in communication with the epidemiologists, probably.
Yeah, but it stopped, and probably we should keep in contact. And
Right.
But yeah, we talked about those with them, and also they gave us some feedback how they see it, and they were quite interested in this work. However, of course, this is developed by civil engineers, transportation engineers, and in order to fit it to their needs, I guess there need to be some common work done.
So you mentioned that you weren't displaying the uncertainty, and I presume that uncertainty that you weren't displaying was on the sort of the output graphs, right?
Yes.
How would you model the uncertainty of the agents themselves? With distribution?
Yeah, I think it depends what uncertainty you mean. I think what's done right now is for each simulation run, when you don't, I think, what was it done? What you can do, let's say this. So what you can do is you can recreate this synthetic population every time. I think here we didn't do this, but I have to check if this synthetic population is generated for every simulation run or not. That's I have to check. So I'm not sure about this anymore. But you can have both options. So you can use the same population again, or you can give them other roles more or less. The
And
next
so
run.
what would vary between simulations then? Their choices?
Yeah, the choices. So the choices vary anyway because this is what's actually optimized. Now the choice: should I pick up first the child or should I go shopping first? I have to do this on my list more or less. When should I do it? How can I get there? What makes me most happy? So they have this utility function in mind that every agent will optimize for themselves, which makes it very costly to run these simulations.
Right.
So every agent more or less decides for his day how he will structure it, what might be the best way to do this. Should he go shopping here or should he go shopping somewhere else? And also it takes into account the other people's potential behavior. However, what it's not changing is, I guess, in this case, then the role of the agent. So this will be the same, but he optimizes it in itself more or less every day. What other might be, what you can change is the synthetic population so that the agent first lives here and works there, but then in the next run, it might be a different agent. He lives in the same region, works in a slightly other region. So but this is due to the synthetic population generation.
Right.
Not sure if this was a little bit more confusing than explanatory.
Yeah.
That's
Well,
more confusing. No.
in my reception, I think it was. But so can you distinguish between what we'd call the epistemic and the aleatory kind, or it all has to be the same? Sort of.
I think it's hard to distinguish. Yeah.
Okay, so that brings me to the killer question, which is reminded of us by David Anderson, who said about network models that Monte Carlo methods on network models are really they're not very good at finding the weak spots, but somehow terrorists were really good at it, at finding those weak spots. And so my question is, it seems clear that this kind of model that you're describing would be great for an epidemiological model, but it would be perhaps terrible for a terrorist, anti-terrorism style model, right? Because
yeah, that's for sure. Yes. Yeah.
a terrorist would have his agency is a little different from everybody. He's not minimizing the trip; he's minimizing something else or optimizing something else. So I guess you could have a terrorist agent, though.
Yeah, I guess it depends on the terrorist attack. Now, when you like to see what has the biggest impact in transportation, then the question is which train station might be the most vulnerable, in this sense. And then you can...
Well, in Japan, they've actually had biological terrorist attacks. They were contaminating food or something, and spreading disease, is a time-tested method of warfare. So I would expect that somebody's thinking about these dark thoughts out there.
Yeah, I guess you can also use this. You can reverse engineer it and find the biggest clusters more or less, and then attack those and see. Okay, for instance, in Zurich, there might be the airport or the main station where a lot of people actually every day commute because those are the big hubs here.
Right.
And yeah, then I guess you can get the biggest cluster out of those.
Yeah.
But again, I guess terrorist attack, there's not so much data. And what this model is, again, is for transportation engineers, and they'd like to see the average daily commute more or less so that they can predict where should they change a road, and they're not looking into extreme events. So this model are not designed for those extreme events or very rare events.
Right. Okay. Thanks. Simon, you're You're mute, Simon.
I'm muted, it's fine. Yeah, I think that's all the questions, unless anyone wants to quickly jump in. Yeah, right. Thank you for giving your presentation. I'll end the recording and that formally ends the session. Just want to say, whilst you're here, we have another talk next week